Here we look at two permutations of the letters A, B and C. The permutations A, C, B and B, C, A are different. However, A, C, B and B, C, A are the same combination because A, C, B consists of the same letters as B, C, A. So the order of arrangement of the letters does not matter when we're talking about combinations. As long as the letters in both permutations are the same, then we have the same combination. Now we're going to look at all the permutations of the letters A, B and C, taking two of them at a time. So this is something we did already. We have three ways to select the first letter. So the first letter could be A, could be B, or it could be C. After we've selected the first letter, we have two ways of selecting the second letter. So if the first letter selected was A, we could have AB, or we could have AC. If the first letter selected was B, we could have BA or BC. If the first letter selected was C, we could have CA or CB. So you see we have 6 permutations. 3 ways to select the first letter, 2 ways to select the second letter. By the fundamental principle of counting, we have 3 by 2 ways of selecting 2 letters from the letters A, B and C. 6 ways in total. Actually, you can see that it's the same number of ways of arranging the 3 letters A, B and C. If we just hook on the remaining letter in each of these permutations, we will have the 6 permutations of all the letters A, B and C. Because 3 by 2 is the same as 3 by 2 by 1. 3 factorial ways of arranging 3 objects. Now suppose that we're interested in combinations of the letters A, B and C, taking 2 at a time. So as I explained earlier, AB and BA are different permutations, but they're the same combination. So I'll highlight these in green. So these are the same combination. So we can just write down AB for one of the combinations. AC and CA are different permutations, but the same combination. So we can just write down AC. Finally, we have the permutations BC and CB. They're the same combination, so we can just write down BC. So we can see here that we have 3 combinations. We see that the letters in each combination is different from the others in at least one letter. Notice that to get the number of combinations, we have to divide the number of permutations, which is 6, by the number of ways of arranging the objects in each permutation. So the number of ways of arranging 2 objects is 2 factorial. So to get this number, we have to take the number of permutations, which is 6, and divide it by 2 factorial. 2 factorial is the number of ways of arranging 2 objects, as we've seen in earlier videos. 2 factorial is just 2, so we get 6 divided by 2, which is 3. So 6 permutations is twice the number that we need, because each permutation appears twice. AB and BA, and then we have AC and CA, BC and CB. So we have twice as many combinations if we just say 6. So we need to divide by 2. In general, we know from a previous video that the number of permutations of n objects taking r at a time is npr. So in the example we just did, n is 3 and r is 2. So we had npr, 3p2. And we know what that is. We start with 3 and we multiply back, so we just have 2 numbers in our multiplication, because we have a 2 here. We can also write this as 3p2. It's just on calculators it often appears as NPR like this. And we know that that's equal to 6 in our example. The number of ways of arranging r objects is r factorial. So r is 2 in the example we just did. So we have 2 factorial, which means we take the 2 and multiply it back all the way to 1. That's what factorial means. So we have 2 by 1, which is 2. And we know that to get the number of combinations, we divide the number of permutations by the number of ways of arranging the objects in each permutation. So we have to take NPR and divide by R factorial. That's how we get the number of combinations. So NPR is 6, and we divide by R factorial, which is 2, and as we've seen before, we get 3. So this is just some notation. You will probably see this notation on your calculator, but this is the notation that you normally see in books, and this is the notation that we will be using quite a lot. So in our example, N was 3 and R was 2. So we would read this as 3C2 or 3 choose 2. We're choosing 2 objects from 3 objects, and each combination is different from every other one. So at least one object in each combination differs from objects in all the other combinations. So just to go back over this again, 3C2 is given by 3P2 all over 2 factorial. So we see whatever number's on top, which is 3. We multiply back towards 1, but we want the same number of numbers on top as this value here. So if this is 2, we need to have 2 numbers on top. And we need to take the factorial of this number. So this number is 2, so we have to write 2 factorial here. So of course we know what we get. We get 6 divided by 2, which is 3, as we've seen a few times already. Let's just consider another example. Let's look at 4C2. This is the number of ways of choosing 2 objects from 4. It's the number of combinations. So we have 4 on top here, so we start with 4, we multiply back towards 1, but we just have 2 numbers on top because we have a 2 here. And then we divide by this number factorial, 2 factorial. Let's look at 7C3. We start with 7, and we multiply back towards 1, but we have to have 3 numbers on top. So we have to 7 by 6 by 5 on top. This number on top is 7P3, as we've seen in the previous video. And underneath, we have the factorial of this number. So we have 3 factorial, which of course is 3 by 2 by 1. We have the same number of numbers above as below. Let's look at 10 choose 4. On your calculator, you would put in 10, then you would press the NCR button, and then you would press 4. So we start with 10, and we multiply back so that we have 4 numbers on top. So we have 10 by 9 by 8 by 7. And we have 4 here, so we have to have 4 factorial underneath. Well, 4 factorial is 4 by 3 by 2 by 1. So we have 4 numbers on top and 4 numbers underneath. So let's just work this out. We have 4 2s are 8, 3 3s are 9, 3 7s are 21, 21 times 10 is 210. Now here is a very relevant example. It is the number of combinations of the numbers 1 to 45 taking 6 at a time. So this is the number of ways of doing the current national lottery. There are 45 numbers, we have to select 6 of them. And of course we're dealing with a combinations problem, because each set of 6 numbers has to differ from every other set of 6 numbers by at least 1 number. In the last video, we calculated the number of permutations of 6 numbers from 45. That was 45 PR. So, well, where R is 6. But of course, we did not divide down by the number of ways of arranging 6 numbers, which is 6 factorial. So anyway, let's go through this. So, like you saw in a previous video, we had calculated 45 by 44 by 43 by 42, by 41, by 40. But we now need to divide by 6 factorial. 6 by 5, by 4, by 3, by 2, by 1. So again, you see we start with 45, we multiply back towards 1, so that we have 1, 2, 3, 4, 5, 6 numbers on top, because we have 6 here. And then we have to divide by the factorial of this number, 6 factorial. So you can work this directly out in your calculator using the NCR button. So there are 8,145,060 different combinations of 6 numbers from the numbers 1 to 45. So you can choose as many as this number of combinations when you do the lottery. And of course only one of them is the winning combination. Let's look at this example here, 4C1. Well, we could apply our rule. We calculate 4P1. Basically we start at 4 and we multiply back towards 1 so that we just have one number appearing in our calculation. Well, if that's the case, we'll just have 4 appearing. We just want one number appearing on top. And of course we divide by this number factorial. So we divide by 1 factorial. Well, 1 factorial is just 1. So 4 divided by 1 is 4. So we see that 4C1 is 4. And that makes sense, because the number of ways of choosing one object from 4 objects is obviously 4. So if we have, say, the 4 objects or the 4 letters A, B, C, and D, and we want to get the number of ways of choosing getting combinations of the 4 objects, taking one object at a time, well, we just have A, B, C, D. These are our 4 combinations. They're all distinct, of course. So we don't have to look at 4C1. We could have looked at 5C1 or 6C1. In general, NC1 is just N. N is the number of ways of selecting one object from N objects. That sort of makes sense. By definition, we say that if we take any number and choose 0 objects from it, we say that there's only one way of doing that. So this is really to do with a formula for NCR, which I won't go into in this video, but I might cover later on. So the number of ways of choosing 0 objects from 4 is 1. The number of ways of choosing 0 objects from N objects is 1, by definition. From now on, instead of, say, talking about the number of combinations of 3 objects, taking 2 of them at a time, I will talk about the number of ways of choosing 2 objects from 3 objects. So implicit in this statement is that we are talking about combinations of 3 objects taking 2 at a time. We are not talking about permutations. Anyway, here's an observation. This hash symbol just means number of. The number of ways of choosing 2 objects from 3 objects is equal to the number of ways of choosing 1 object from 3 objects. Well, we know that the number of ways of choosing 2 objects from 3 objects is 3C2. So let's work this out. We start with 3 and we multiply so that we have 2 numbers on top, because we have 2 here, and we get 2 factorial, which is 2 by 1. Working this out, we get 3, as we've seen before. Now let's write out the number of ways of choosing 1 object from 3. Well, that's 3C1. Well, we covered this earlier as well. We take any number, choose 1, we just get that number. We basically get 3 over 1 factorial, which is 3. We just get this number. Well, let's write out the number of ways of... Let's write out all the combinations of 2 objects from 3 objects. Suppose that the objects we use are the letters A, B, and C. Now we've done this already. So let's write out the 3 combinations of 2 objects, or 2 letters from the letters A, B, and C. Well, AB is one combination, AC is another combination. So we just take, say, A and combine it with B, and then we combine it with C. So we get two different combinations. After we are finished with A, we look to the next letter, which is B. We do not go back and combine it with A, because that would give us the same combination as AB. We just look forward from B, so we combine B with C. Then we would go to C and look ahead from C, and there's nothing ahead from C. So here are the three combinations. Now let's consider number of ways of choosing one object from 3. Well, this is easy. We just have A, B, or C. We have 3 of them. But notice that when we choose 2 objects from 3 objects, we have 1 object left over. So when we choose AB from A, B, and C, we have C left over, which is here. And when we choose AC from A, B, and C, we have B left over, which is here. And when we choose BC, we have A left over, which is here. Similarly, if we have, say, 5 objects or 5 letters, suppose we have A, B, C, D, and E. Well, the number of ways of choosing 2 objects from 5 is the same as the number of ways of choosing 3 objects from 5. Because if we choose any 2 of these objects, or these letters, suppose we choose A, B, then by default there are 3 left over, C, D, and E. Here I have written out all the combinations of the 5 letters taking 2 at a time, or I've chosen 2 letters from the 5 letters. That's another way of putting it. You just take A and combine it with all the letters that are ahead of it, B, C, D, and E. Then you move on to B and combine it with letters that are ahead of it, C, D, and E. Do the same for C, C, D, C, E, and then eventually you get to D, and you have D, E, and that's it. You're finished. So all of these are different. And you can see that there are 4 and 3 is 7, 2 and 9 and 1 is 10 combinations. We calculate 5C2. We start with 5, multiply by 4, and divide by 2 factorial. And we have 20 divided by 2, which is 10. To get 5C3, we could do something similar. We could take 3 of these at a time. However, we only have to write in the remaining letters here. Like if we have A, B here, then C, D, E is what is left over. If we take A and C, we have B, D, E. If we take A and D, we have B, C, E. If we take A and E, we have B, C, D. We get all these different combinations in blue. So when we choose 2 letters or 2 objects from 5 objects, by default we are also choosing 3 objects from 5. If we work out 5C3, we have 5 by 4 by 3 all over 3 by 2 by 1. 3 factorial in the denominator, and the 3's cancel. So when these two numbers sum to whatever this number is, of course 5's have to be the same, and when these two numbers sum to the number above, then the combinations are the same.